So while everyone settles in. So I will talk about the dark polynomial commitment scheme, which is a polynomial commitment scheme built from groups of unknown order and using some of the VDF techniques. And especially I will talk about improvements to that commitment scheme, how to make it better, faster, safer, smaller, darker. What is a polynomial commitment scheme? Well, a polynomial commitment scheme is just simply a commitment, and it's usually you want it to be shrinking, so it's a small value, and it has additionally, and it's binding, so if I commit to one polynomial, I can only open to that polynomial. And additionally, it has a fast evaluation proof, so sort of a very custom special snark that I can prove to you that the polynomial evaluated at a point has a certain value, and additionally that the degree of the point polynomial is bounded. And these polynomial commitment schemes, and I will not talk about this at all, but they're very important. Why are they important? Well, because we can build snarks from them. And especially all of the trusted assumptions, all of the cryptographic assumptions, then only are in the polynomial commitment scheme. Everything else is information theoretic. So this means that if we have a polynomial commitment scheme without a trusted setup, for example, then this gives us a snark without a trusted setup. And all of the efficiency kind of comes from, or most of the efficiency now comes from just these polynomial commitment schemes. So your snark is going to be as good as your commitment scheme. So how do we, I will quickly go over how the dark commitment scheme works and then how we can improve it. So the core idea of the polynomial commitment scheme, and I already mentioned groups of unknown order, is that we can encode a polynomial as an integer. So how do we do that? Well, we simply write so this is a polynomial over a prime field, and then we pick a point q that is larger than the prime. So, and then we can encode the polynomial by simply evaluating the polynomial over the integers at this point q. So, as an example, if I have here f of x equals 4x cubed plus 2x plus x plus 3, and my p is 5, and all of my coefficients here, right, I can write them as less than 5. And then if I evaluate it at 10, you know, this has an in decimal representation. This looks very nice. It's just simply 4213. You notice that the size of this encoding is at least, it's at least the size of the polynomial itself, but we'll resolve that later. But the nice thing is that, it's easy to show that every integer in 0 to q to the d plus 1 can be decoded to a polynomial. So I can encode and then uniquely decode it. And I can also deal with positive and negative coefficients. Why is this encoding interesting? Well, it has nice homomorphic properties. So first, you can see that it is additively homomorphic, at least up to a point. So if I have f of q and g of q, I can compute f plus g of q, and this is the same as f of q plus g of q. So example here, we have our 4231, and then we have the polynomial 1443. You can immediately see, like, you can in your head decode this. It's very easy. And if you add them, you get 5674. Do the decoding in your head and get 5x cubed plus 6x squared plus 7x plus 4. And if you had first decoded the integers and then added the polynomials, you would have gotten the same result. So this only works if q is large enough, right? If there's no overflow. So we have to pick a q that is large enough to support all of our homomorphic operations. Additionally, there's a multiplicative, or we really care about the monomial homomorphism. So if I multiply the polynomial by x to the k, then in the encoding space, this is equivalent to just multiplying the encoding by q to the k. So here, the example, if you want to multiply by x squared, you multiply by 100. So now we've mapped our polynomials to integers with these nice homomorphic properties. Now how do we shrink them and build a commitment out of them? This is where the cryptography comes in, and this is especially where these groups of unknown order come in. So these groups are, we use them as a map, they're especially homomorphic maps, so we just compute g to the x for an integer x, and this maps me to a group element, so it's shrinking. And under computational assumption, or this is under basically under the unknown order, the assumption that G is a group of unknown order, it is hard to find a collision. So I will not find two integers that map to the same group element. Of course, this can only be computational now because this map is shrinking. But again, this map has additive homomorphism. So if I have g of x times g of y, this is the same as g of x plus g of y. So now this gives us our commitment algorithm for the polynomial commitment. So I just take my polynomial, lift it to the integers, and then compute c equals g to the f of q. And we already talked about these groups of unknown orders, and if we use class groups, then this gives us a commitment scheme without trusted setup. So let us look at so how do we, what is missing? What is missing is an evaluation protocol, and I will only give you basically half of the evaluation protocol, mainly a proof that the polynomial is of degree d. You can then later on easily append this to show that in fact the polynomial is correctly evaluated at a point. But say I want to prove to you that this polynomial is evaluated at a point d. And note that what I will present here is slightly different from what is in the paper. And this is because the improvements kind of build on this. So what I will do is I can split my polynomial into the odd and even coefficients, right? In the paper, we split it into left and right coefficients, but equivalently, you can split it into odd and even coefficients. So the red coefficients are the even, and the blue coefficients are the odd coefficients. And then this equality, which is used in FFTs and things like phi, is that you can write f of x as f even of x squared plus x times f odd of x squared. And then the prover can just simply, and f even and f odd are degree d over 2 polynomials, right? I started with a degree d polynomial. Now I have 2 polynomials of degree d over 2. I will send these polynomials to the prover will send the polynomials to the verifier. The verifier will send a random challenge alpha. And then we continue the protocol on the random combination between f even and f odd. So I will compute f prime of x, which is a degree d polynomial. And now x prime is being set to what used to be x squared. Okay, so I exchange x prime with, I replace x squared with x prime. I just reinterpret it. And we obviously want to do, so if we do all of this with our commitment scheme, we just have to map everything to our encoding space. So instead of sending the polynomial itself, I send you a commitment to the polynomial. And because of the additive and the multiplicative homomorphisms, I can actually do all of these checks and perform all of these operations just over the commitment scheme. So the important thing that the verifier needs to check here actually is that that this second line here holds, okay? So that in fact f of x, or the commitment to f of x, is equal to the combination of the even or and the odd coefficients, so that the polynomial is correctly split up. And this just results in this green check. So I need to check that I use the multiplicative homomorphism. I need to check that C, the commitment to the polynomial, is equal to CE times CO to the Q. And already as a preview, I will outsource that check using a proof of exponentiation. And one more thing. So in every round, the degree shrinks by d over 2. So I do this for log rounds. Okay, I'll do this for log d rounds. And I always replace my q with q prime. And so in every round, the q that I use doubles. So I start with some q, which was my original coding. Then in the second round, I use q squared, then q to the 4th, q to the 8th, and so on, up to q to the d over 2. And how large does q need to be? Well, as I already said, whenever all of these operations are over the integers, there's no field arithmetic here. So when I take this random linear combination, my coefficients grow by a factor of alpha. So if my challenge is drawn from 0 to the p, where p is the size of my field, or it's drawn from 0 to 2 to the lambda, then this is roughly by how much my coefficients will grow. So what does this mean? It means that basically I need to set my q to be larger than p to the... It turns out you need 2 log d, because you also lose in the extraction a little bit, but basically you need to set your q to be p to the 2 log d. So what does this mean? How many bits does q have? Well, if p has lambda bits, then q has log d times lambda bits, roughly. Okay, so it's blown up a little bit. But and then how does the final step of the protocol work? Well, the prover sends now has a commitment to just a constant degree polynomial, and it's just sends over that constant. And then the verifier, very importantly, needs to check that this constant is small enough. So why does it need to do that? Well, basically, it needs to decode it and check that, in fact, this is a constant polynomial. And the way to do that is just simply to check that f0 as an integer is small. And then you can check that c is equal to g to the f0. So all of this gives us, proof, and you basically in every round you have to send 2 group elements. And the way that I already mentioned this, the problem is that, so the problem with this protocol as presented is that this green check gets more and more expensive. Why is this the case? Well, q grows in every round, and it actually the length of q doubles in every round. I start with q, then q squared, q to the 4th, and so on. So in the end, the verifier would need, if he wants to check this, he would actually need to do an exponentiation with a d bit, with an exponent that has d bits, and that it takes work linear in d. And part of the reason why I want the polynomial commitment is to actually outsource work and not have the verifier do work that is linear in the size of the polynomial. But, you guys are all experts in this. We can actually outsource this using, for example, Benjamin's protocol. And I see that it should be 256-bit group exponentiation. But basically the idea is that, I run this PoE with the prover and the verifier, and I just get a proof that, in fact, this exponentiation was done correctly. And of course, I present everything here as interactive protocols. Under the Fiat-Shamir transform, you can make all of these non-interactive. So what does this proof of exponentiation look like? Well, the high... I'll try to keep the idea short. Basically, the idea is that the verifier will send. I claim that x to the alpha is equal to some y. The verifier will send a lambda bit prime l, and then the prover Peggy computes the quotient and the remainder, and sends over a commitment to the quotient, and then the verifier can check that in fact, that alpha is in fact can be decomposed into this quotient and this remainder. So this protocol is secure under the adaptive root assumption, and it is efficient if alpha is smooth. And in our case, alpha is smooth. Alpha is q to the d or something like that. So the problem, though, is that basically q, and we'll get into this a little bit more, but you have to think about what the size of q is. And q is really, so this small q here is really exactly the same size as alpha. And even if alpha is smooth, so if alpha is 2 to the k for some k, then this doesn't mean that that Q is going to be smooth, right? Because I'm doing Euclidean division here that, it doesn't, I have no guarantees about what structure little q has here. And that is going to be a problem, because now let's look at the prover cost of this protocol. So I'll make everything a little bit smaller. So basically the commitment step, so this is in every round. In the first round, I have to commit to a polynomial of degree d, and this can be done in d steps. In the second round, I have to commit to a polynomial of degree d over 2, but the coefficients are twice as large, so this is again d. And then the third round, it's, the coefficients grow a little bit, but the size of the polynomial shrinks more and more. And overall, this takes me basically lambda d steps, but only if I've pre-computed the powers of g to the q. So why is it important here that I pre-compute the powers of g to the q? Well, the coefficients in the beginning, they're just lambda bits, right? But q is log d times lambda bit. Q is much, much larger. So if I just did the naive way of computing the commitment by just computing g to the f of q, then this would A, be sequential, which is a problem. But B, it would also take me lambda d times log d time, because q is larger. And if I use this multi-exponentiation technique, then I get the cost down to be something linear. Unfortunately, though, there's the second part of computing the PoE, and that basically, if you look at it, there's no way to, or the way that this is done, I cannot, even with multi-exponentiation techniques, even with pre-processing, because I have no guarantee about the smoothness of this quotient, I get something where the prover work is actually d times log d, and this is d times log d group operations, or group exponentiations, which is actually significantly worse even than other snark proof systems. And this factor of log d, there's a factor of 20, like these things actually matter. And then there's constant of 2 or so, and then 40 or 60 or something. So these things tend to matter. So let's break down the cost a little bit more and see maybe what we can do about this. So in the first round, so this is all of the PoEs that I need to compute. So in the first round, I have this commitment here, my odd commitment, which has d over 2 lambda bit coefficients. And then I need to raise that to the q and compute my PoE. And the expensive part here is always going to be computing the PoE. So basically, even if I run this down, in every round my q gets larger and larger, but and the coefficients of the polynomial get smaller and smaller, but the expensive part here is always computing the PoE. And especially, and again, right, why is this expensive? Well, this is very hidden in the exponent here, but again, it's because I have to compute this quotient, divide by this challenge L, where, sorry, I have to divide by this challenge L, where the sort of the smooth integer gets spread out. So there's another, we have another proof of exponentiation, or VDF construction, by Christoph. And how does this Pietrzak PoE work? Well, it works slightly differently. So the idea is basically that if I have, again, I have a smooth exponentiation, I want to compute x to the 2 to the t to the y, the idea is that I just simply split this up into two statements. So I send you the statement, I send you z, which is x to the 2 to the t over 2. And now I have two statements. So x to the 2 to the t over 2 equals z, and z to the 2 to the t equals y. And both of these things together imply the original statement, right? So I now have just simply two statements, but the nice thing is now I can combine these statements into one statement, just again using a random challenge alpha, And here I take a linear combination between these two statements and get one statement with one exponentiation. And evaluating this statement has half of the complexity and exactly the same form as the previous statement. So I can just recurse this for log t rounds and in the end check the final step or the final squaring myself. And this protocol is secure under the lower order assumption. The problem is, it turns out that if we use this, we could improve the prover time. The problem with this protocol is that now this has log t complexity. So if I, in every round, have to run a protocol of size log d, then my overall proof size would be log d squared, so it would blow up. You know, the verifier time would blow up as well, or would increase as well. So this is not something that we want. But maybe we can somehow combine these things and resolve this. And the main thing that we're going to do is look at this upside down. Well, so yeah, no, upside down. So big difference. Right, so you know, we just look at this from the first statement, which comes from the last round of the dark protocol. But we can do all of these PoEs at the end. It doesn't matter whether we do them in between or whether we do them in the end. But this statement, which is now at the top, is the most complex statement, right? It's an exponentiation of size q to the d over 2, and then they successively get easier. And so then the next one would be q to the d over 4. So this lets us build, you know, use sort of these darker PoEs, where the idea is that we can actually run the Christoph's protocol, we can run the Pietrzak PoE to, in each round, reduce the first line to a statement that looks like the second line. So we can just run one Pietrzak PoE for all of these statements together. So what does this look like? Well, I now have to do an exponentiation with q to the d over 2. So I will just send you some the half of the statement. So the same as in the Pietrzak PoE, I will send you q to the d over 4, or c0 to the q to the d over 4. And this is now exactly, this reduces the problem to a statement which I had already wanted to solve in the next round of the dark. Okay? So what I do then, I take some random challenges, alpha and beta, and combine the first statement with the second statement. And I can do this basically over and over again. And the nice thing is that now computing all of these commitments turns out to be actually quite easy. Why is this the case? Well, in the first round, it turns out that these polynomials they have very large, you know, they might have a very large degree, but they're super sparse. They actually just have one coefficient. In the second round, the same thing is, right? You know, the exponent, the degree is huge, but the sparsity is low. And there's actually this trade-off where, you know, the lower we go, the degree gets smaller, but the sparsity shrinks. And it turns out that we can, so if we look at these statements, we can actually, you know, in the first round, we have one coefficient. This is the proof elements that we need to compute. And then after log d over 2 rounds, we have square root of d coefficients. So we could either compute this by doing the multi-exponentiation with square root of the d coefficients, or we can do a direct exponentiation with q to the square root of d, and these things are roughly the same cost. And then for the later rounds, you know, the final thing is just an exponentiation by q, which is cheap anyway. So what does this mean? It means that, and you know, I went over this very quickly, but I hope you can maybe believe me that the overall cost now is actually just square root of d. There's no, I don't have to pay because I do basically one way going up to the halfway point and then the other way to going down, and it turns out that the overall cost is just square root of d. Oh, seems like I have the same slide twice. So, and you know, we can even further improve the protocol because I still have there's still a, now I reduce the cost of these PoEs to be something that is square root of d. So what is the remaining cost? Well, the remaining cost was committing to these polynomials, and this took linear work. And basically, I won't get into the details, but the core idea of the main protocol was to split the polynomial into two parts. It turns out that we can actually use a similar idea. We can split the polynomial into k parts in a very similar way. So not just the odd and even coefficients, but the coefficients that are 0 mod k, 1 mod k, 2 mod k, 3 mod k, up to. So I split the polynomial into k parts, and while I'm committing, I'm doing some pre-computation. Basically, I'm computing all of these fi polynomials. I'm just committing to these, and then it turns out that from these commitments, well, this animation should have appeared first. So during the commit, I compute all of these I pre-compute the commitments to these sub-polynomials, and then I store them. And it turns out that during the protocol, from these CIs, I can reconstruct whatever commitments I need. And this is the original commit phase, still has to be linear work. But it turns out that, and I need to store some things. I need to store k things. But basically, if I set k to be equal to square root of d again, then it turns out that the entire open protocol will or the eval protocol will again be square root of d work, because I can reuse these pre-computed values during the opening phase. So what is the end result that this gets us? Well, I now have a new commitment scheme, or this darker commitment scheme. The work is, I said, the commitment work is linear in the degree. It actually is even just linear in the sparsity of the polynomial. So if I have a polynomial with a bunch of zeros, then this becomes even easier to commit to. And then the eval protocol is basically, it's square root of d times some log factors. The CRS, so I need to pre-compute these powers of g to the q. It turns out that with this optimization, I only need to store square root of d of them. So I don't need, say I have a degree million polynomial. I just need to store 1,000 things, roughly, which is much better, even especially if I implement things on hardware. The proof size grows by 1 group element per round, but and the verifier is still very efficient. And most of these operations are multi-exponentiation, so I haven't factored in that you can use things like Pippinger's algorithm to basically get another log factor here. And we have some Philippe from Findora has done some great work on already starting to implement these things just in Python. And the main thing to see here is that things are indeed faster even in practice, but there's a lot more work to do. But the cool thing is that this change that we were working on actually has an additional bonus. So as some of you may have already noticed, is that yesterday there was a paper that came out on using hyperelliptic curves, so elliptic curves of higher genus, to construct groups of unknown order. And these are very exciting because the element representation is just 303 bits compared to I think 1,500 or 1,600 bits for class groups, or 2,000 or 3,000 bits for RSA. But the problem is that the adaptive root assumption and even the small order assumption doesn't hold. So in particular, you can find elements of small order. And this kind of destroys it for VDFs, because it means that, at least with the proof systems that we have now, and maybe this is also some exciting new research area, but with the proof systems that we have now, the uniqueness property of the VDF breaks. So I can convince you that something is the output of the VDF when in fact it's not. But with these changes that we make, and with using some new working a little bit harder in the proof, we can show that darker in fact is secure under the plain RSA assumption and Fiat-Shamir. So, and this assumption is, well, we believe since yesterday to hold in this group. Obviously, you know, this is like very highly experimental, but, you know, at least there's so far no known attack on, on these groups. But, you know, even I mean, in general, Justin talked in the beginning about having better assumptions, and, you know, the RSA assumption is probably one of the most classic assumptions that we use in public key cryptography. So it is cool that we don't have to, you know, that these changes not only make it better, faster, now smaller, but also safer. So thank you very much. And yeah. Any questions? Ellie?
Just about the last thing, I also asked Justin on Twitter. The paper from yesterday mentions there is a polynomial time algorithm to find the order.
Right.
Nothing about
So as far as I know, and everything that I know comes from Dan, is that you know, this is basically the Schuh's algorithm, which we use to count points on elliptic curves. It gets basically worse and worse, or the polynomial, it's a polynomial time algorithm, but the polynomial gets worse and worse with the genus of the curves. So it's like the exponent of the polynomial is like 3 times the genus. And then, you know, you don't need to set the genus to be that high to get basically 2 to the, like, assumed 2 to the 120-bit security. So it is not exponentially secure, right? But the assumption or the hope is that it has security, concrete security, 2 to the 120 or whatever. And it also, you know, it also turns out that basically, if we make the genus higher, the elliptic, the discrete logarithm problem also gets higher. So we don't have to use such a large field anymore, right? We don't have to use a 256-bit field anymore, but we can use we can define these curves over smaller fields. So I don't know. I mean, I think that fine-grained crypto in general is, you know, it seems like a really exciting area, and that hopefully this can get us, you know, very, very efficient things like this. But obviously it's highly super novel, fresh off the presses, and needs more eyes to look at it. Thank you.